Alright, so let's talk about the different types of astronomy. There's different types of wavelengths, so there's different types of astronomy. Radio astronomy is fairly easy to do on Earth. Radio waves can pass through the atmosphere without a problem. So can light waves. So you set up a telescope, you can capture radio waves. The problem with radio waves is that they have the largest wavelength, which means in order to capture them properly, you need a larger telescope. Another problem with radio waves is that they could be coming from somewhere very, 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 very far away. So therefore it would be faint, so again, you need a larger telescope. The telescope shown here is actually in Puerto Rico. It's the largest telescope on Earth. The problem with this telescope, as you can kind of see, where it is. You can't angle this sucker at all. So wherever it's looking, that's where it's looking. So whatever is 20 degrees overhead, that's what you can see. This radio telescope, on the other hand, looks like you can move it. Kind of looks like something from Star Wars. But anyways, it's a radio telescope that can be moved. Now, again, the great thing about radio astronomy is that you can do it from Earth fairly easily. The atmosphere doesn't reflect it, it doesn't scatter it. The radio waves can go through clouds and rain. The sun doesn't interfere with it. It's just easy to get here. With the radio waves, we've actually found that things do emit light through radio waves that are very weak. So you might not be able to see it any other form of EM, but in radio waves you'll be able to see them. And sometimes things are just not hot enough to emit visible light or any other type of light. And so you don't get to see it. But if you shoot a radio or get a radio telescope, you might be able to collect and see the radio waves. So here's an example of what you can see with a radio telescope that you normally couldn't. This little bit in the middle, the kind of little black glowing line there, that's a visible galaxy. So if you were to look at it through an optical telescope, that's what you would see. However, you point a radio telescope at it and you get these lobes, these blue, green, red emission lobes. And those are radio waves coming out from the galaxy. Now, obviously, the radio waves are not red and green and blue. Red just means you've got a lot more radio waves coming from it, and blue means you have less radio waves coming from it. Okay, so it's called false coloring. And these things are called radio lobes, large jets of gas coming from the center of a galaxy. So sometimes these large radio telescopes are just not ideal. What you want might be smaller radio telescopes, and that's what you're seeing here. Smaller telescopes kind of in a line collecting radio waves, so you can get a more detailed image. Doing this with all the small radio telescopes, you're doing something called interferometry. And basically, you're taking all of the pieces of the radio wave that you can collect and piecing them back together. You can also do this with visible light. All right, so the Earth's atmosphere lets through visible light, some infrared, and radio waves. Right? It blocks everything else. So if you really want to get the infrared or the UV or the gamma rays or the X-rays, you have to get up past the atmosphere. So for infrared, because it only blocks some of it, you don't need to get up too far. Okay, so you can actually make an infrared telescope and attach it to a balloon, like a giant weather balloon, or you can fly it in an airplane and collect more information. Or you could send it out into space to get even more information. So here's some pictures with infrared. Okay, so you can see the A is optical or visual, and B is the infrared. A lot more detail, right? Same C and D, right? C, that's a picture of space. Looks kind of cloudy, lots of dust. But when you look at it through the infrared, you can see it much clearer. So, 2003, there was actually the Infrared Space Telescope, the Spitzer Space Telescope. It's not getting any interference from the Earth because not only is it above our atmosphere, but it's not orbiting the Earth. It actually orbits the Sun. So we're not blocking its way. There are some pictures from that. UV, ultraviolet telescopes. These have to get above what we like to call the ozone layer, right? Because the ozone layer actually forms by taking UV light and combining it with oxygen. And so it's literally taking it out and not letting it go through to us. So we have to get a telescope above the ozone layer. And once we do, well, we can see things in the UV. Okay, now you want to talk X-rays and gamma rays. These guys are super short wavelengths, which means they've got a high frequency, a high energy, and they're absorbed completely by the Earth's atmosphere. Right, so again, the Earth's atmosphere has a high opacity to X-rays and gamma rays. So you have to get your telescope out into space away from the atmosphere. And what's interesting, and it's kind of hard to think about, but there's things out there that are too hot to glow. Which is kind of crazy because usually you think as things get hotter, they glow brighter. Well, there's actually things out there that are too hot to glow in the visible and will only glow in X-ray and gamma rays. Okay, great. So let's just make a telescope, send it out there, and look at those guys too, right? Yeah, it's just not quite that easy because anything we send out there, the mirrors are just going to take. So if we send a traditional one out, like a Hubble, for instance, Cassegrain, where it bounces off the mirror, it won't bounce off the mirror. The mirror will just take it. And then you'll be left with no picture. Whew. So what do? You have to have what's called nested mirrors. And you have to get them at such an angle that as it comes in, yes, it does hit the mirror, but it kind of just grazes the mirror so that you can get some of the light to bend towards focus. And we created one of these guys in 1999. So this is a picture of an X-ray, or X-rays emitted from a supernova, a star exploding. And we'll get to these at a later chapter. But look at the temperature. The gas at the edge has 50 million kelvins. 50 million. I remember boiling of water, it's like 373. And we're talking 50 million. These are things that are so hot you can't see them. Now there's a little white dot right in the center there. And that's not a piece of dust on your screen. There's actually a little white dot in this picture. And we think that you were looking at a picture from space, you are looking at a black hole. You have just seen a black hole. Isn't that cool? Okay, so your textbook will tell you gamma rays are not very awesome. Well, it'll say that we still don't know a lot about gamma rays. We do know more than they're letting on. But this is a picture of a gamma ray. There's two different ones. There's Compton gamma ray and Ferma. Right, and so this is another picture of a supernova. In this case, we can't really see a bright red dot, or sorry, bright white dot that may represent a black hole. It's just an explosion of a star. All right, so here's just a comparison straight from your textbook, the different radiation, different things that you need to think about, and then some applications. And lastly, I just love ending on this picture. It shows you all of the different views of the same galaxy. So the first one's radio, B is infrared, C is the visible, D is X-ray, and E is gamma. Just take a second to look. If you just look through the optical, the visual, what you would be missing. So what you see is not always what you get.